Why does time move forward? You might think clocks create time. They don't. Clocks only show it. The real reason time feels one way is something else entirely, entropy. And once you understand entropy, a lot of strange things suddenly make sense. Why the past feels fixed, why the future feels open, why you can remember yesterday but not tomorrow, and why reversing time is almost impossible. Now pause for a second because this question sounds simple. But inside it is a paradox that quietly bends your definition of reality. Look at what everyday life does without you noticing. Things always drift in one direction towards spreading out. Hot coffee cools down. Perfume spreads across a room. Ice melts. A glass falls and shatters into pieces. But the reverse almost never happens. Cold coffee doesn't spontaneously heat itself. Perfume doesn't jump back into the bottle. Melted water doesn't calmly gather itself into a perfect ice cube without a freezer. Shattered glass doesn't leap up from the floor and rebuild into a flawless cup. We call this obvious. We call it normal. We don't even question it. But physics forces you to ask the dangerous question, why is that normal? Because here's the twist. If you zoom in to the microscopic level, atoms colliding, molecules bouncing, forces acting, many of the fundamental equations don't actually forbid running time backward. In a lot of cases, if you filmed a scene and played it in reverse, the equations wouldn't scream impossible. They'd still work. So why does real life scream fake the moment you see a reversed video of broken glass reassembling? Why does everything in your experience insist on one direction? Two facts are colliding here. The basic laws can be time-symmetric in their mathematical form. Your lived experience is time asymmetric in every practical way. In your experience, the past is filled with evidence. The future isn't. The past leaves marks. The future doesn't. The past can be recorded. The future cannot. So is time a force? Is there some invisible engine pushing reality forward? A Feynman-style answer would start by correcting the question. Time isn't a force. Time isn't an engine. There is no time wind pushing you into tomorrow. What you're really observing is this. Systems naturally move from rare special states into common, typical states. And that movement has a name, entropy. But the word entropy is a trap. People hear it and immediately jump to vague words like chaos or randomness or disorder. Those words can point in the right direction, but they don't explain anything by themselves. So let's do what Feynman always tried to do. Throw away the vague word and build a clear picture. Imagine a brand new deck of cards, perfectly ordered. That exact order is special. It's rare. Now shuffle the deck once. Shuffle again. Shuffle again. The order disappears quickly. Now ask if you keep shuffling randomly. Could the deck ever return to the exact original perfect order? Theoretically, yes. Nothing in the laws of motion forbids that exact arrangement. It's not impossible. But practically, it's so unlikely that your brain calls it never. And that's the point. Perfect order is one needle in a giant haystack of possible arrangements. Messy arrangements aren't one thing, they're millions of different patterns. So when you shuffle randomly, you aren't choosing disorder. You're just wandering around the space of possibilities, and almost all of those possibilities look disordered. Now connect that back to time. When you watch hot coffee cool down, you're watching a system move from a special concentrated energy state to a more typical spread out energy state. When you watch perfume fill a room, you're watching molecules move from a special all-in-one-place state to a typical everywhere state. When you watch glass shatter, you're watching a system move from a highly organized structure to a typical scattered configuration. And you are labeling that direction forward in time. But the deeper claim is more shocking. Time's arrow, the reason forward feels real, is not produced by clocks. It is produced by probability. Probability of what? Probability of arrangements. Probability of microscopic configurations. which means we have to stop talking about entropy as a mood word and start treating it as a number, something we can count. So in the next section, we'll do exactly that. We'll take entropy out of mystery land and turn it into a simple counting problem using a box and a handful of balls. And once you see entropy as counting, time's direction stops being magical. It becomes almost inevitable. Let's make entropy simple in one sentence. Entropy is counting. If you can't count it even roughly, you don't really understand it. So imagine a transparent box. Draw an imaginary line down the middle, left side and right side. Now place 10 little balls on the left side. The right side is empty. That's a very ordered situation. 10 on the left, 0 on the right. Now shake the box gently. Balls bounce. They collide. They move randomly. After a few shakes, what happens? You rarely see 10-0 again. Instead, you start seeing 7, 3, 6, 4, 5, 5. Most of the time, it hovers near an even split. And the key question is why? Does the universe prefer balance? Does nature love symmetry? No. Don't give nature feelings. The real reason is brutally simple. There are far more ways to be mixed than to be perfectly separated. This is the core idea behind entropy. To understand it, we need two concepts. A macrostate is the big picture you observe. 5 balls left, 5 balls right. A microstate is the exact detailed arrangement underneath that macrostate, which specific balls are left, which are right, and where exactly they are and how fast they're moving. The macrostate is like saying the room is messy. The microstate is the exact position of every sock, book, and cup. Now here's the punch. A macrostate with more microstates is more likely because there are more ways for the system to be in that macrostate. Let's compare two macrostates, 10-0, all 10 balls on the left. 5-5, 5 balls left, 5 balls right. How many ways can you get 10-0? Essentially one way, all are left. How many ways can you get 5-5? You can choose any 5 balls to be on the left. Even before you think about exact positions and speeds, the number of combinations is huge compared to one. And if you include the real microscopic truth balls can sit in countless positions. With countless velocities, the number explodes. So when the box is shaken randomly, the system isn't trying to reach 5-5. It's simply moving around randomly, and the region of possibility space labeled 5-5 is enormous, while the region labeled 10-0 is tiny. That's entropy. Entropy measures how many microscopic realizations are compatible with what you see macroscopically. Now take this idea and upgrade it from balls to molecules. Hot coffee cools down because energy spreads from a concentrated region, the hot coffee, into a larger region, the room. There are countless microstates where that energy is spread out across the room, and far fewer microstates where it is neatly concentrated back into the coffee. So could the room's random molecular motion, by pure chance, coordinate itself and push energy back into the coffee, reheating it? The laws don't strictly forbid it. But the microstate count is so ridiculously unfavorable that it's effectively never observed. This is why time's arrow feels real. You are not witnessing a fundamental time force. You are witnessing the near certainty of drifting from rare states into typical states. Now you might ask if it's just probability, does that mean reversals are possible? In principle, yes. If you waited long enough, random motion might briefly produce a rare arrangement again. But long enough becomes a terrifying phrase when you are dealing with trillions upon trillions of particles. The number of microstates is so astronomical that possible and practically impossible become two totally different worlds. This is why broken glass reassembling isn't just unlikely, it's absurdly unlikely. The number of microstates corresponding to shards on the floor is overwhelming compared to the number corresponding to perfect cup on the table. Now here's the bridge to the next mystery, memory. Because memory is physical. A memory is a pattern stored in matter neurons, ink, silicon bits. Creating and stabilizing that pattern requires energy. And energy use creates heat. and heat increases entropy. So if time's arrow is entropy's arrow, then memory should be tied to entropy too. That would explain why we remember the past and not the future. And that is exactly what we'll unpack next. Now we get to the part that makes this topic feel almost unsettling. We remember the past. We don't remember the future. And it's not just human brains. The world itself is filled with records of the past, photographs, fossils, tree rings, scars, footprints, cracked paint, worn steps on old buildings, and even light traveling from distant stars, carrying information from events long ago. The past is everywhere. But the future? There are no physical traces of it. You don't find tomorrow's newspaper lying on your table today. You don't discover next week's photo already saved on your phone. You don't remember a conversation that hasn't happened yet. Why? Here's the key idea. Information is physical. Information isn't a ghost. It isn't abstract in the way people casually speak about it. To store information, you must store it in physical states, ink on paper, magnetization on a hard drive, voltages in a memory chip, patterns of synapses in a brain. And changing physical states costs energy. When you take a photo, the camera isn't just capturing an image. It is running electronics, moving charges, flipping bits, burning battery energy, and producing heat. When you write a note, you are rearranging molecules in ink and paper, burning calories, producing heat. When your brain forms a memory, neurons fire, chemicals move, energy is consumed, and heat is released. In every case, recording information is a physical process that typically increases entropy in the broader environment. This is the crucial connection. To create a stable record of something, you must interact with the world in a way that spreads energy and increases entropy. So the act of creating memory itself rides on entropy's arrow. Now consider what a trace of the past really is. If a glass shatters, it doesn't just become pieces. The event produces sound waves, vibrations, heat, dust, scattered light patterns, tiny scratches, and pressure marks. The environment becomes stamped with evidence that something happened. That evidence exists because the event unfolded in the entropy-increasing direction, energy spread out, particles dispersed, information leaked into the environment. A past event leaves traces because the world is constantly producing traces as it moves toward higher entropy. But a future event hasn't happened yet, so there are no traces to leave. And you can't have the trace without the event, because that would mean effects exist before causes. So the absence of future memory is not a mystical rule. It is a consequence of how physical records are made. You might think, but couldn't the future leave traces if time were reversible? In a purely time-symmetric universe, with no special boundary conditions, past and future would be less meaningful. But our universe has a special feature. It began in a remarkably low entropy state. That gives the world a direction in which entropy increases. That direction defines what we call the future. And because record-making increases entropy, records form in that direction, meaning records point backward to the low entropy side. That's why memory points to the past. Now connect this to why time reversal feels impossible. To reverse time for a system, you don't just reverse the big visible objects. You must reverse every microscopic detail, the exact velocity of every molecule in the air, the exact pressure waves in the room, the exact heat distribution in the walls, the exact scattered photons moving away from the event. If you don't reverse all of that, traces don't untrace. The environment remains stamped with the past, and the system redrifts toward typical high entropy states. This is why scrambled eggs don't unscramble. It's not that physics laws forbid it. It's that the number of microstates associated with scrambled is insanely large compared to perfect egg, and you would need microscopic control beyond imagination to guide the system back. Also, chaos enters the picture. Many macroscopic systems are highly sensitive. Tiny differences grow over time. Even if you could attempt a reversal, microscopic errors would amplify quickly and destroy the reversal. So entropy gives you the probability slope, and chaos makes that slope even more unforgiving. Now we're ready for the final lock. Why the universe has this arrow in the first place, why the early universe matters, and why time reversal is mathematically allowed but physically unrealistic. That's what we finish with next. To fully understand time's direction, you need one more idea. The arrow of time doesn't come from the equations alone. It comes from the starting condition. If you start a system in a rare low entropy state, the overwhelmingly likely evolution is toward higher entropy. That's not philosophy. That's statistics. Think back to the box of balls. If you start at 10-0, the system drifts toward 5-5. If you start at 5-5, it can wander both ways, but it tends to remain near typical mixed states because typical states dominate the space. The direction becomes obvious only because of where you started. Now apply this to the universe. Our universe appears to have begun in an extremely low entropy state. That doesn't necessarily mean neat in the everyday sense, but it means that the initial configuration was rare in the space of all possible configurations. From that rare beginning, the universe has had an enormous number of ways to become more typical, more spread out, more structured, more entropically rich. This is the deep reason time feels one-directional. We are living on an entropy gradient. Now about reversing time. Movies show broken glass reassembling, smoke going back into a cigarette, spilled water leaping back into a cup. Your brain instantly labels it fake because you're sensing the missing microscopic story. When the glass shatters, the environment changes too. Air molecules move, sound waves spread, heat diffuses, photons scatter. A true reversal would require not only the glass pieces to fly back, but every microscopic ripple in the environment to reverse with perfect precision. That's the key. Time reversal is not rebuild the object. Time reversal is reverse the entire microstate of the universe in the region. And even if the fundamental laws allow it, the probability of the environment spontaneously doing that is essentially zero. Worse, chaos makes the challenge brutal. In many systems, tiny errors grow exponentially. So even if you tried to set up a reversal, microscopic imperfections would explode into macroscopic failure almost immediately. You can visualize it with a pool table. Imagine you break a perfect triangle of 100 balls. They scatter everywhere. Now imagine you want them to return into a perfect triangle without touching them, just by letting physics run in reverse. To do that, you would need to reverse every collision with perfect precision, every ball's exact velocity, every angle, every spin. A microscopic error in one ball ruins the entire return. So yes, reversal is mathematically allowed. But physically, it is so fragile and so unlikely that possible becomes practically meaningless. Now let's wrap this into one clean takeaway you can keep forever. Time feels like it moves forward because entropy tends to increase from a low entropy start. That single idea explains why hot things cool down, why smells spread, why broken objects don't self-repair, why the past leaves records, why memory points backward, why the future isn't remembered, why reversal looks fake, why forward feels real. Clocks don't create time. They measure change. And the change you notice is change that typically increases entropy. So the next time you watch coffee cool, or perfume spread, or ice melt, don't treat it as boring normal life. You're watching the universe reveal its statistical signature, the arrow of time. Here's the final recap in the simplest possible form. Clocks don't generate time. They track motion and change. Entropy measures how many microscopic states fit what you see. Typical states have vastly more microstates than rare states. Systems drift from rare to typical because probability favors it. Recording information costs energy and increases entropy. That's why the world is full of traces of the past, not the future. Time reversal isn't forbidden. It's statistically and practically crushed. If this finally made time's direction feel obvious, write one line in the comments. Entropy equals counting. And if you want the next mind-bending episode, we can go deeper into the next step. Why empty space isn't empty, and why you never truly touch anything, even when you think you do. Because once you start memorizing physics and start seeing the ideas clearly, reality becomes simpler and stranger.